Alrighty, this is the fourth video on solids of revolution, finding their volume. We're going to go ahead and do something similar to what we did in video number 3, where we're going to use the same several functions and their graph that I've already printed out, and talk about a couple of different scenarios. Okay, let me see. I think it'd be better if I zoomed in just a smidge. Okay. Okay, let's go ahead and identify the functions first. We recognize the fact that this is the green function, similar to the last time, except for it's moved over to 2 instead of just moved over to 1. This is y is equal to x minus 2 squared. Okay. We recognize this linear right here is x over 3, or 1/3 x, doesn't really matter, it's the same thing. And let's do the trig function in red, which I think is rather apropos. So y is equal to 2 sine pi over 4x. Okay, now what I've done by putting pi in there in terms of the horizontal change in shape is I've now created a sine function whose period is actually a number of integers long. It's actually an 8. The period is actually 8, because notice the first hump goes from 0 to 4. Its complementary down hump would go 4 to 8. Okay, so basically your b value has provided the pi, and therefore you've transformed it from a trig evaluation along the x-axis to integer evaluation along the x-axis. That was done on purpose so we could actually have a little bit of fun with it right here. Now, let's go ahead and for our first one, oh gosh, what do you say? Okay, well, let's go ahead and let's be predictable, that's fine. Let's go ahead and deal with this right here, okay? And let's actually revolve that around the x-axis. Now the problem is that you're going to have a hard time finding that point of intersection and that point of intersection, okay? And this is something that I did this on purpose because I wanted to go ahead and I wanted to be able to figure out, I want to basically show you how the workings of the calculator, okay? So here are the two functions that we're dealing with. I basically turned off the linear in the y equals so that we could actually just focus on these two. And I need to calculate their points of intersection, okay? When I calculate their points of intersection, that second calc, okay? See, calc goes right above the trace. You press the blue button, the second button, and press that. So second trace gives you calc. And you see down here you have intersect at 5. So press 5, and it's going to give you what that looks like a little flower, okay, on one of the curves. Go towards the intersection that you're looking for. Get close to it, press enter. It'll give you another flower on the other curve, pretty close to that intersection. Press enter, and it says, hey, is that your guess? And you press yes. And it'll basically, using an algorithm, it'll actually give you a decimal approximation, and that's to 7, looks like 8 decimal places for that. Now, I've told you this before, but the great thing about this is that your calculator has now stored that particular value in for x. So if you go back to the main screen, you can press X and it gives you that same approximate answer. Now, since this is the left-hand side of the interval, I would go ahead and take that answer and I would store it. Store is this button right down here, if you don't remember. Press STO, and then you can actually store it into any one of the letters. And since we're used to using A for the beginning of our interval, let's store it into A. Okay, let's go back to the graph, and let's find the other point of intersection. Okay, let's go over on that same curve with the flower towards the other point of intersection. Okay. and it gives us 3.1259123. Now your calculator has stored that value in for x, and we can go ahead and take that answer and store it into the letter that we're used to using for the right-hand side of an interval, which is b. Now that I have stored both of those in, okay, I now need to start looking for how to set up my integral. Now, big R and small r are actually going to be relatively easy since we're dealing with around the x-axis. So basically, big R and small r are just going to be the same as the representation of the function. So basically, just the x expression, the variable expression. So big R, the curve that is farthest away from the axis of revolution, is the red one. As it spins around the x-axis, that red curve right there is going to form the outer shell of that solid of revolution. That is why we can sort of visualize it and see that our big R is going to be 2 sine pi over 4x, and r squared is 2 sine pi over 4x squared. Or if you want, you can do 4 sine squared pi over 4x if that makes you a little bit happier. Okay? Obviously, small r has to do with that quadratic, and it is x minus 2 squared. Again, my r is already squared, which is why it's easy to accidentally plop that into the integrand if I were not in the habit of actually making this table and knowing that small r squared is actually x minus 2 to the fourth. This goes in the integrand, this goes in the integrand, okay? Now I know pi from a to b, okay, of 4 sine squared pi over 4x minus x minus 2 to the fourth dx. Now here's the thing. I'm going to go ahead and let you look at that for just a quick second. Okay, actually I'll go ahead and move that up for those of you that want to continue to look at it. I have stored those functions into y3 and y1. So I could actually accomplish this integral by having pi times the integral. Now, I'm going to actually use a and b. And when I want to do the integrand right here, I know that y3 is the trig function, but I know I need it squared. And I know that y1 is that quadratic, but I know I need it squared. And that should be the volume of revolution of that particular area. And of course, on the AP exam, they want us to either truncate or round to 3 decimal places, which is why I had to do that for several years, so you got into a nice habit of doing it. That is our answer. Okay, and that's a nice example of one that required me to use my calculator in order to find the limits of integration by finding the points of intersection. And you will be asked to do that on the AP exam, and by then you should have it down, and it actually should be second nature, should be habit. Okay. Okay, let's go ahead and move on, and let's do a different one. What do you say we do? Let's use the linear. Again, I like to use the red for the trig, and then we'll use the blue for the linear. And I want to take this region and, let's see, just to be difficult, let's go ahead and spin it around. Oh, I don't know. How about y is equal to 3? Sound good? So y is equal to 3 will now be our axis of revolution. I'm going to spin it around there. Now, First of all, we need to find the interval. The interval ought to be pretty easy on the left-hand side. Those obviously both go through the origin, okay? The problem is this right-hand side. That's probably not going to be a rational number, okay? So let's go back to our calculator, okay? I am now going to go down and I'm going to turn on the linear, go up on top of the equal sign and turn off the quadratic. And now I need to go ahead and graph. There's my linear. And then here comes my trig function. Those obviously both go through the origin. I can actually numerically verify that. That really isn't all that big of a deal. But I do need to find that point of intersection on the right-hand side. So let's go ahead and do that very quickly. Okay, let's go ahead and zip on over here. Okay, and it's 3.2669. Okay, remember, that stores it into X, so I can go here, see that it's there, and store it into B. Okay, now, I can, and I should, when I'm actually writing stuff out and showing my work on the AP exam, I should go ahead and write it out as an approximation, although I should never use that number. I should always use the exact value that I've stored into my calculator. Now, I know that as it revolves around y is equal to 3, the outer shell of that solid of revolution is going to be this linear, okay? And remember when I said that your radius is always going to be axis minus function or function minus axis, and it always depends on which one's going to give you a positive answer. And you always want to subtract the smaller number from the larger number. So big R is 3 minus x over 3, and big R squared is 3 minus x over 3 squared. Small r is going to be 3 minus 2 sine pi over 4x, and therefore small r squared, and if this isn't just kind of notationally just kind of a pain in the rear end, I don't know what is, and that should be it, okay? Now, I can do this in my calculator, okay? But I'm going to show you basically what's going on first here. I'm going to write it out. 0 to b, okay? And then I'm going to have r squared, which is 3 minus x over 3 squared, and then r squared, 3 minus 2 sine pi over 4x squared dx. Now, can I still use my y1 and y3? Yeah, you just have to use a bit of parentheses, and it's still probably going to be beneficial to do it. I just need to remind myself where they're stored. So I go to y equals, and I recognize the fact that the linear is y2. The trig is y3. Okay, so let's go pi times the integral from 0 to b, and then I'm going to put parentheses. I'm going to go 3 minus y2 squared minus 3 minus y3 squared. And then I'm going to do that with respect to x, and it winds up being 34.609. So approximately 34.609 is basically what's going to be going on right there, okay? That brings us pretty close to the end right here. I'm going to do one more video because there's one thing that I've left undone so far, and I may use the printouts that I already have of the functions that we've been playing with. But the last thing that we need to be doing, and the thing that we'll cover in the fifth video, is revolving things around vertical axes rather than horizontal ones. Okay, so stay tuned and look forward to that.